Good afternoon, everyone, and thank you for joining us today. So today we're going to go into a topic that is fundamentally reshaping the vehicle architecture and safety, the high-performance computers. So as we all know, vehicles nowadays are getting more and more sophisticated and basically are relying a lot into software-defined platforms. So the security of their central processing units becomes something absolutely critical. So over these next 40 minutes that we are going to be talking here, we are going to go through the evolution of the distributed ECUs to centralized HPC architectures. We are going to define what constitutes an automotive HPC and examine the specific threat vectors targeting these systems. And finally, we're going to touch the guiding role of the key standards like ISO 21434, UNEC R155, and definitely at the end, some business benefits regarding it. So let's start first with a brief introduction about us and about AVL, the company which I belong to. So AVL is the world's largest independent company focused on development, simulation, and testing all types of powertrain systems. They go from combustion engines or to hybrids and as well nowadays hydrogen solutions. So we cover the full spectrum of different engines that are existing. And we partnered with different global automotive and mobility industries. So the idea is to drive innovation towards a safer and better future of transportation. Moving beyond towards what AVL is at glance, AVL was founded in 1948, and we have more than 75 years of experience with a presence around the world in 29 countries and a lot of, let's say, global tech centers and engineering centers with more than 12,000 employees. Most of us engineers, and basically more than 2,300 patents here. With respect to Plaxidity, as I said before, we partner with different global automotive and mobility industries, and this includes as well PlaxidityX, the company that was previously known as Argus Cybersecurity. The idea was to work into cybersecurity for vehicle engineering. So let's say combining the expertise we have in AVL with Plaxidity security solutions, the idea is that we are going to improve the security by design of different customers we might have, meeting critical regulations like UN R155 and building trust into the connected automotive technology that we're having nowadays. Then entering into the topic, let's say that I will start with this slide that is mostly going to show what is part of the electrical and electronics architecture that we have currently in the market. So it's something very traditional that we have right now still, in which a vehicle electronic system were very decentralized. So you have sometimes many ECUs, sometimes 100 individual ECUs, all of them handling a specific task like an engine control module, gateway, window lifts, etc. And all of them communicated via CAN, which is a robust kind of bus, but at the same time, it was bandwidth limited. And with this, then they rely into physical isolation and they have limited connectivities, and therefore the attack surfaces for these units was a little bit less. Then, just 1 second, I cannot find my mouse here. With the driven demands of the ADAS systems and high infotainment systems, V2X communication, which is coming very soon as well to be implemented in many vehicles, and the complexity of many software features, then we are going to move towards a consolidation on a centralized computer. So we are still having domain controllers, different ones, and as well the combination with high-performance computers. These high-performance computers are acting as integration hubs, in which basically they are connected mostly by using high-speed buses like can be Ethernet. This means that we are going to have more features like can be over-the-air, let's say, updates, and as well maybe complexity of or more complex fusion of different sensors for autonomous driving. This is, of course, increasing then the security, let's say, potential security vectors, or let's say attack vectors, sorry, that we can find there. At the same time, then the idea is to go or move towards a very or a full centralized high-performance computer, like a one brain that will absorb all of the different ECUs that we currently have, and it will be connected directly to the different actuators in order to fulfill the vehicle functions that are defined there. But then let's go towards the definition of an HPC. What is actually an HPC? We are talking about a complex system on chip, or let's say a multi-core CPUs, or that can have as well GPUs in order to render different graphics like we can find in the ADAS systems. And some of them even right now are adding dedicated cores to AI. This HPC can manage mixed criticality workloads in which we can find then safety critical functions like governed by standards like the ISO 26262 that many people in safety know, running as well with non-critical infotainment applications that they are all running in the same high performance computer as we saw before. Then they are going to be using automotive Ethernet, let's say, interfaces. At the same time, they are going to be sharing accelerators. They are going to be sharing storage, and at the same time, they are going to be sharing different other type of buses for image processing and so on. Then, at the same time that we are adding all of these functions in just one high-performance computer, we are talking about that the software stack is getting as well complex, or is becoming more complex, and therefore it will involve a lot of, let's say, new things or new features like can be the hypervisors in order to handle multiple operating systems or guest operating systems like can be AutoSAR or QNX or Linux or Android Automotive, something that Victor will show ahead in his slides. Then this heterogeneity and the different, let's say, components that we are going to have from different vendors at the same time will increase the complexity of integration and definitely more challenges towards security specifically. Then moving towards the evolving threat landscape. So more power, more connections equals to bigger risk. So continuing what I was saying before, we are going to have more connectivity, expanding more the attack surface, and therefore more concerns regarding vulnerabilities, mainly into the connectivity. So cellular modems, Wi-Fi stacks, Bluetooth implementations, V2X, that will be used a lot in the future. Therefore, adding more with respect to the physical access, not only to access via wireless, but as well physically with OBD ports or USB in order to try to perform attacks towards, I don't know, flashing the firmware or manipulating the bus directly. This adding as well something that sometimes we don't take into account, that is the supply chain. So many of the different vendors are as well using third-party software libraries that sometimes are not well, let's say, sanitized, and that can introduce as well more vulnerabilities towards the product. Attacks might not get directly into the HPC, but as well they can go towards the inputs. Sometimes the attackers might not reach the HPC, but they can reach as well the inputs, like can be GPS or even the cameras or any other component that can be managing some of these applications to actually cause a potential impact that can be very severe into systems like, for example, the ADAS one. This means that systems like the ADAS one that currently are managing, I don't know, steering or braking, etc., can as well be manipulated and therefore cause potential very severe issues. On the other hand, as well, we are having other systems that are not that critical for the security of the person itself, or the driver itself, but as well to the vehicle, because some of them are integrated the security of the vehicle itself, like, for example, unlocking the doors, or either intercepting different CAN messages to perform other type of attacks, like, I don't know, accessing the vehicle only to steal something, or even leaving it unresponsive for some time. Specifically for the HPC, something that with the experience that we are having as well with different customers, something that is very high risk and that is something that we have to take care a lot about is with respect to the privilege escalations across the different domains. It means that then attackers can take care or can take advantage of low criticality functions and going toward, like, for example, infotainment applications, and going more towards trying to affect other safety critical functions. For that, then, many of them are implementing the so-called sandboxes. Moving to the next slide, what are going to be here the security challenges for automotive HPCs? First, securing such HPCs represents a very significant challenge because of the complexity of the hardware itself, of the software from numerous suppliers. You can find in the same one, I don't know, suppliers like from BlackBerry, QNX, you can find Linux, you can find Android Auto, and all of them running at the same time. And then managing these dependencies and ensuring that the interaction across the different components is handling very well is actually very, very hard and very critical to do. There is therefore a tension between performance and security as always. So we are going to have a lot of cryptographic operations, memory protection mechanisms, and runtime monitoring that all consume CPU and all consume as well memory and all consume as well power. So therefore, the idea is to have them as well constrained, but at the same time, this represents then, let's say, an impact into the user experience. Another thing is with respect to the lifecycle management. As we know, then the vehicles can have life cycles that go between 10 to 15 years or more, and this requires then robust solutions for throughout all the life cycle that can go from secure update mechanism along with as well long-term vulnerability management strategies, which is part of the process that goes outside of the vehicle itself. This is consuming as well in a lot of time of resources, not talking only about the resources of the vehicle, of the ECU itself or the HPC itself, but as well of the human resources that are all working into a specific project. Another thing is, as I said before, is with respect to the supply chain and how, for example, vulnerability in third-party software activities are managed that actually are very integrated, or how is that we ensure that the system on chip or the SOCs that we are using, the actual electronics that we are using, then is not suffering for any kind of potential security breaches, and how is this done among different HPCs we can find in different type of vehicles. And almost the last one is with respect to the mixed criticality. As I said before, we are having different type of functions running different partitions, how we can then ensure that these different critical applications or the criticality of different applications will not interfere with other ones. And then talking about the separation of different environments. Finally, the most important one, which is basically the cost, is always something that is very important for the companies, specifically nowadays, and in the automotive sector. And then implementing, let's say, comprehensive security measures definitely requires more expensive hardware, more sophisticated hardware, like, for example, hardware secure models, and increasing as well the testing complexity. So it's a lot of, let's say, of resources from a cost factor or money factor that has to be implemented here. Moving then towards the essential mitigation strategies, because we have seen already what are going to be the potential threats, but how we can then mitigate these potential threats. And then let's start with something that is regarding about part of the process, which is the security by design principles, something that must be embedded throughout the development process in order to ensure that we are developing a secure product. On the other hand, we are finding a lot the implementation of hardware secure models. Let's say that we are having a dedicated secure microcontroller integrated into the board itself that is providing a hardware root of trust. It handles secure generation of keys, storage, cryptographic acceleration, many other, let's say, features that we can find regarding authentication and as well secure boot. Is basically designed to be tamper resistant and quite important. Therefore, moving towards secure boot to ensure the authenticity and integrity of everything what is running into the high-performance computer, together with trusted execution environments, a topic in which I'm working very actively right now, on my experience in which we are going to be working in the creation of isolated environments to run sensitive application or security services that can be protected by any kind of compromised operating system. So try to basically isolate the potential breach that we might have. Not less important is the memory protection units and the memory management units, which is quite important in order to a strict memory isolation between the different processes. And then going as well towards resource partitioning, something that is very or is going to be widely used in high performance computers, according to my experience as well, is the hypervisors and containerization technologies. So containerizing the different operating systems and different applications that are running and are assigned different CPU cores. Moving as well is the secure debug and access control. We are going to have more peripherals and therefore more physical ports available and more applications that might introduce debug functions and how we can control these debug functions. We're going to find as well that due to the high performance that they are providing as well, finally we can implement an intrusion detection system, which actually is not that developed and not that, let's say, implemented into vehicles nowadays. And this will help also a lot to monitor Ethernet traffic and monitor as well anomalies that may be present in the system. The secure communication, of course, is very mandatory. I have a colleague working actively in secure onboard communication and the MACsec as well from an Ethernet perspective, because the idea is to ensure always the message exchange between the different HPCs or HPC combination with other ECUs that might be still available, ensure the message integrity and authenticity. And of course, something that is quite important and is a feature that is being offered nowadays is the over-the-air updates, which has to be as well secure, and therefore we have to ensure that we have a secure backend infrastructure providing such type of service. And on the other hand, as well, that we have some reliable rollback mechanisms in case of failures. Something quite important, which is in which me and my team mostly is specialized, is the threat analysis and risk assessment, something that currently is coming as well, or very well defined in the ISO SAE 21434, in which we are providing, the ISO is providing us a framework in order to work about how we can analyze and therefore improve the what is going to be the evaluation of the risk management across the whole life cycle of the vehicle and the development, and as well aftermarket. Then this is forcing a lot of the organizations to implement a very structured process and process-oriented approach towards the cybersecurity. Jumping then towards what is going to be the vulnerability management is a lot of exigency towards, as I said before, not only resources in the vehicle, but resources outside in order to manage all the time what is going to be the potential vulnerabilities and what are going to be the different incident response processes that has to be put into place. These may be using, I don't know, the CVEs or any other type of, let's say, of processes that might be implemented in a company to actually handle very well or handling in a better way the incidents. Jumping towards the network segmentation, something that we find in electrical electronics architecture that is very important when you are designing your internal architecture into the vehicle, where you're going to place the different components, and therefore where you're going to place something quite important like can be the firewall. And then jumping towards the logging and monitoring, something that, as I mentioned before, and the vulnerability management and implementation of SOCs. This as well is quite important. How is this handled into the HPC? How is it going to be handled outside? The same with respect to isolation between software domains, something that maybe we can go deeper in another session. Then what is going to be the role of these standards and regulations we're having? Because currently many of these standards were studied when we were having basically the electrical and electronics architecture driven by ECUs only. Now we have that there are rules that are legally binding many markets like the United States, European Union, Japan, South Korea, and so on, in order to implement and maintain a certified cybersecurity management system. Here, therefore, it's quite important to go towards the risk management into the company. So a lot of processes that the company has to put into place. And the impact with respect to high performance computers, it goes more towards the expertise of each one of the people that are performing this threat analysis and risk assessments, for example, or dealing with different systems. So how much experts they can be in order to handle this type of, let's say, of functions. On the other hand, going towards or practically impacting a lot what the current analysts might have with respect to threat analysis, what they have to expand into their knowledge, and this is even going beyond towards the potential threats. This, of course, with the exigency of a cybersecurity management system by the I-155, that is basically driven as well by the ISO 21434. So in this case, compliance is no longer an optional, it's a prerequisite in order to access different markets. And the impacts of having, of course, different, let's say, or introducing HPCs is not only with respect to implementing these regulations, but as well into how the organization is going to change. So many OEMs nowadays, and as per my experience, are having a lot of difficulties into making changes into their organization, and this is affecting at the same time the potential development processes. This only to enforce the minimum security requirements. So a lot of effort and minimum security requirements that we might have there. So in order to wrap up and then pass the word towards Victor, I just can, to summarize, say that the high-performance computers are, of course, revolutionizing the automotive capabilities and represent a very big concern into the, let's say, into the risk that we are seeing in the vehicles nowadays, specifically for the connectivity and a lot of functions they can handle. They can be a single point of failure, for example, if it gets involved into any specific type of attack. You can have then a vehicle non-operational just for maybe a simple type of attack. On the other hand, securing automotive HPCs demands a holistic defense in-depth strategy and deeply integrated hardware security features in order to actually ensure that the product is being developed accordingly. This as well with respect to the implementation of a nice architecture in which we are having a partition of the electrical electronics architecture, and on the other hand of the architecture of the HPC itself, how you are implementing hypervisors, how you are using different guest OS, how you are isolating these different applications that might be safety and security critical. What are you implemented in order to improve, let's say, the logs that you are getting due to the, monitoring and so on. So this is a task that is going very far and beyond, because it requires a continuous vigilance, so a lot of resources, as I said before, and compliance with the different standards. And on the other hand, as future challenge, we are having the introduction of artificial intelligence, and specifically into the ADAS systems, and that is going to go beyond. And on the other hand, we're having another challenge that is going to be the quantum cryptography, up to when these algorithms that we are using for cryptography are going to be helpful, and how is that maybe adding more complexity from the cryptography perspective to this HPC can help us to combat these potential machines outside. And finally, one of the evolving attack vectors, as per my experience in a previous as well conference in which I was with respect to poisoning the different models of AI. So currently, a few models are being used, all of them implemented into different, potentially into different vehicles. Maybe one simple attack can affect all of the different vehicles. With this, I close then, and I pass the word to Victor.
Thank you very much, Javier, and thank you for the great presentation. Let's now zoom out a bit and have a look at the security solutions from the vehicle and fleet point of view. As you can see here, there are several ECUs with different solutions and potential different logging mechanisms. I will speak about already existing state-of-the-art solutions that can be used to prevent attacks, and to monitor the vehicles and fleet. Now, let's imagine a vehicle with a TCU that is provided from a specific tier 1, the gateway, the main gateway that you see here provided by another tier 1, ECUs that are with AutoSAR, that are with Linux, that are with Android and QNX. All of them could have different logging mechanisms that can generate integration issues for the OEM and a great amount of data. This will then impact for sure the bandwidth and all what is being pushed to the cloud by generating in the end cost and a lot of work and unneeded investigations that will need to be performed as part of the VSOC, VSIM, XDR, call it as you want. This is one direction of the complexity that is now coming in the automotive market because of the new HPCs that are being more and more deployed in the market. Looking at from a different angle, and also Javier already mentioned it, that for all the vehicles now, in order to be type approved, you need to fulfill the UNR regulation. But what does it really mean when we speak about security and monitoring what's happening with the vehicles? You can see that it's clearly stated that the vehicle manufacturer will need to include the capability to analyze and detect cyber threats, vulnerabilities, and cyber attacks from vehicle data and vehicle logs. So this is mandated. OEMs need to react to that, need to prove it to the auditors when they need to fulfill the type approval. Now, let's speak a bit about the challenges that we at PX observe when speaking about HPCs. So you've seen it from what Javier presented. There are a lot of features that are already needed, that are already being developed, that are already deployed across the different ECUs. But at the same time, we see that there is now an expanded skill hacker base from automotive specific, and it's focused on popular Linux, Android, and Ethernet that also came into the automotive market. The knowledge that was exploited before by the hackers as part of the IT, as part of the telecommunication industry, now it's also useful in a bad way also for the vehicles. On top of that, there are the new safety risks, and I think this is one of the biggest challenges that we see now. The HPCs that are currently mostly developed are an integration between an ADAS and an infotainment or an IVI system, and that is happening because of simple things like having the infotainment connected to the front and to the back camera, and because of that, two ECUs that have completely different requirements like safety and usability are now connected, and then they push for additional risks coming from lateral movement that can be achieved in between these two in between these two virtual machines. On top of that, as I was saying, if there are different ECUs from different tier ones with different logging mechanisms, you will end up with having siloed sensors that are causing limited visibility for cross-domain attacks, and of course they are hard to integrate. Then another one that I was already briefly touching was around VSOC alert fatigue. If you will have different sensors coming from different ECUs with different reporting mechanisms, a lot of security events that are being reported to the cloud, there will be potentially many false positives that are being reported, and then you end up with the risk of having real security incidents that are lost in all this noise that is generated. On top of that, you have the complexity. You have OEMs that need to monitor multiple components with limited or incompatible security measures, as I was mentioning, the safety and usability. Now, knowing the challenges, let's have a look and see what would be the approach to handle them in a holistic way. So in what we are observing currently, the most important thing is to have in-vehicle detection sensors to identify the security events in real time. There is no other way in knowing what's happening with the vehicle, what's happening with each of the HPCs and with specific features. On top of that, you need to have the option to prevent certain attacks in real time. I'm not saying that all of them need to be protected automatically, but some of them, once the OEMs and the tier ones better understand and trust the detection capabilities, some of the actions can be selected to be also prevented in real time. Another important approach in securing vehicles is to have updatable security with rule sets, with configuration, or even with code changes. There is no way to have a rule set or an IDPS or whatever solution that will not need to be updated over time. It's the same case with computers. It's the same case with phones. The security needs to be updatable. Another one is to report the incidents to a VSOC for fleet anomaly detection and threat investigation. Threats that are coming from different vehicles and incidents that are being reported from different vehicles can paint a different picture when you watch it and when you see it at fleet level. And because of that, also actions can be much better pushed from the VSOC side, but information collected from the vehicle and the detection capabilities are really important when we speak about that. Then another approach of having a holistic solution is to break the silos. You need to harmonize the security events from different sensors into a unified source with a holistic view. And for that, there are, of course, solutions. I will speak about some of them in the current session. And then, of course, it's always easier when you go and you have a solution that integrates both the in-vehicle sensors and the VSOC cloud fleet monitoring, because then you can see and you can react. You break away from all the integration issues that you typically encounter when you take different solutions. Now, having a bit more in a detail check, we selected here to explain it on a really complex HPC. You see that we put the cluster, we put a telemetry control unit, we put the ADAS, we put the infotainment, all of them under the combination of a so-called HPC SOC, of course, with the hypervisor that is standing under them and controlling the different virtual machines. And now let's think about what would be useful in such an HPC. Of course, an ideal one with a lot of different ECUs connected. So first of all, you see that you need to have dedicated solutions for detection in all the different operating systems. You cannot ignore some of them. You cannot only focus on AUTOSAR while saying that the Linux shouldn't be monitored. The same with QNX and Android. There are already existing solutions, state-of-the-art solutions that can be used out of the box. And that's something that I'm presenting here. And in our vision, we are splitting that in between detection. For AUTOSAR, of course, there are network IDS and network. When I speak about the network, I mean CAN and Ethernet intrusion detection systems. And of course, the IDSM solution that is already available for most of the AUTOSAR providers. But on top of that, you can have also prevention focused on the CAN and the Ethernet networks. Of course, working with existing solutions that are deployed in the market, like Javier mentioned, having a MACsec doesn't mean that you do not need an IDS that checks what's happening with your network. For Linux, there are even more solutions. Focusing again on detection, there are dedicated host IDS sensors that can be deployed in the network, in the ECUs for monitoring what's happening with the ECUs, for monitoring what's happening with de facto solutions used in the industry like FS-Verity, DM-Verity, SE Linux. There are dedicated solutions that allow you to monitor what is happening and to see that are not disabled. The same IDSM, I'll focus more in a minute on that one. IDSM dedicated to Linux, respecting the AUTOSAR standard. In the Linux environment, we have even protection solutions like platform integrity, system limiter that can be deployed. I'll also speak a bit about them of what they are helpful to. The same for QNX and Android, similar kind of solutions that are available, allowing OEMs and fleet providers to monitor what's happening with the vehicles. But everything needs to connect in between and then also send the data to the VSOC. So for that, we see the need for an IDSR, for a reporter that collects and aggregates and sends the data to the VSOC. Now, focusing a bit about these modular solutions, we see them in 4 different categories. I already mentioned the host protection, the IDSM, IDSR used for logging and sending, transporting basically all the data collected from the sensors to the cloud, and then CAN and Internet protection focused on the network. Now, having a bit of a detailed look on the host protection, this is a solution that is focused on protecting the vehicle and protecting the ECU also during the runtime. So as Javier mentioned, there are already solutions that are deployed kind of in all the ECUs like Secure Boot and so on, but that's not enough. And that's why you need a solution that will allow you to monitor what's happening with your software also during runtime. For that one, you need to ensure the integrity, and then you need to have a platform integrity solution that allows you to trust that your code is not changed also during the runtime. The same with system limiter. There are solutions available on the market, automotive grade OS hardening that prevent unwanted actions, and this is focusing again on preventing certain attacks. The same threat detection, having sensors, it's really mandatory to have them and knowing what's happening with your ECUs. They are available, proven, and modular. So depending on the specific threats that you are defining as part of the threat analysis and risk assessment, you can define what and which feature can be used out of these state-of-the-art solutions. Now, taking it a bit more in detail and focus on what can be such sensors, because typically we manage to deploy the IDSM because that is coming out of the AUTOSAR, but you need also the same for the Linux. So then some examples for the Linux and Android and also KNX are the sensor bundles that we can offer. Some of them focus on the denial of service detection, reconnaissance. So basically, if you see that someone is doing reconnaissance actions to better learn your ECU, there are dedicated sensors for that. Also for bundles, so focusing on solutions that are deployed already in the ECUs for protecting the ECU, like SE Linux, we have dedicated sensors focusing on that. And the same for Android. If FS Verity is used, you need to know what's happening and if someone is not able to disable it. All that can be integrated with the IDSM and IDSR. Additional customer sensors can be built, and there are solutions available for that. Now, because I was speaking a lot about IDSM, about what IDSM means, and about the capability of sending all these logs from the ECUs and from the HPCs, there is a solution available from AUTOSAR that can be reused on all the different ECUs. It's standardized, it's integrated, it allows for event collection and normalization. It can collect all the security relevant events from multiple sources, and it will then normalize them for analysis. It allows for scalable architectures, so supporting both centralized and distributed IDS deployments across the vehicle network. And of course, it allows for secure communication. Now, that's not enough. So collecting the logs and storing them on the ECU is one good step. But of course, after that, you need to send them out of the vehicle. And again, we have standardized solution available from the AUTOSAR. We can reuse it across all the different operating systems. So if you have a telematics unit or a gateway where you want to deploy an IDSR, there are available solutions that allow standardized alert reporting. It's interfacing with IDSM and other components. It allows for event logging and forwarding, and also it supports, of course, the backend integration. Another point for the IDSR and what we see really important as a general rule is that it needs to be customizable. It needs to allow the OEMs and suppliers to define the IDSR implementations with standardized structures. Now, looking a bit about how the IDSM and the IDSR work together, let's start from the left, from the in-vehicle sensors that are deployed in the ECUs. They are identifying real-time events inside the ECUs or in the networks, and then generating security events that are then being collected by the IDSM still in the same ECU, and the IDSM will generate qualified security events that are then pushed either in a persistent memory for forensic investigations or for future collection, or ideally pushed to the IDSR. At the IDSR side, it will collect the qualified security events from all the IDSMs and then send them to a cloud XDR for analysis. There are also different directions as part of the IDSR here to add AI capabilities for doing additional correlation, but considering the current status of the microcontrollers available in the automotive, it's still in the early phases of discussion. Now, speaking a bit about the CAN protection categories, because you are protecting first the ECUs, but you need to monitor also what's happening with the CAN. There are dedicated solutions available on the market for monitoring what's happening with the CAN, for detecting anomalies. Typically, the IDS solutions are built with a library that knows how to detect the anomalies, and an additional rule set that knows how to that allows you to configure and focus only on the alerts that are important for your traffic. Such features for the CAN detection and protection are the specification enforcement. Some example of these features are ID enforcement, signal range check based on the DBC and XML, diagnostics inspection, and some of the features that are under this umbrella are allowed diagnostic services, state-aware diagnostics, so detecting if certain diagnostics are allowed to be run depending on the state of the vehicle, brute force detection performed with diagnostics commands, denial of service detection, reconnaissance detection, and so on. The same for the frame timing analysis. These are more advanced capabilities available already out of the box, like frequency monitoring and cyclic messages injection detection. These are solutions that are already available on the market. It's important for them to not generate false positives. We at PlaxidityX have this as the most important focus on not generating any false positives, because this will go against all the savings that the OEMs can bring out of it. The same for Ethernet. So also on the Ethernet, there are already available solutions on the market that can inspect Ethernet traffic in real time, that can again detect malicious communication based on predefined rules. We believe that currently, considering all the safety implications that we have discussed before, having a deterministic approach inside the vehicle, and especially for HPCs where safety is important, it needs to have the predefined rules that can be updated depending on the additional detections. Of course, also with Ethernet protection, as with CAN, OEMs have the option to decide when to prevent and what to prevent. And also the Ethernet protection solution is built in the same way. Typically, you have an in-vehicle engine that knows how to interpret the traffic, and then with the help of an external tool for configuration generation, a dedicated rule set is being generated. The Ethernet is usually deployed in either gateway domain controllers or in network switches or in connected ECUs. Again, usually these solutions are available for classic AutoSAR, bare metal, or POSIX. It's really agnostic to the different platforms. What's also important for the Ethernet is that you need to make use of the hardware optimization capabilities. Each of the NXP, Marvell, and Broadcom that we are mentioning here have hardware acceleration capabilities, and then the rules that we know are using a lot of processing power can be deployed as part of the hardware accelerators. And with that, I'll focus now a bit on the fast return on investment. So by deploying already available solutions that are built for ensuring a real-time mitigation via detection and prevention of the attacks, you can greatly reduce the costs, and it's mainly the cost that you would otherwise invest in developing the solutions, integrating solutions that are built from different providers, and configuring solutions that generate a lot of false positives. With avoiding this cost, of course, you are reducing the cellular traffic on one end and the cloud storage on the other. You optimize the VSOC fleet monitoring by reducing the false positives alert fatigue. We've seen this as a problem in the industry as part of our VSOC activities. We know how to reduce it, but we also know how to configure our products in order not to generate false positives. And for sure, you will be future ready with updatable protection, so the vehicle stays secure for years to come. The way to do that is by understanding attacks that are, some of them happening in different areas of the world or in specific architectures of the vehicle. And then with that information, you can easily update the rule sets. I think that's about it. Now a very short introduction about PlaxidityX, just explaining why we have this knowledge and why we want to share it with the industry. We currently have more than 72 million vehicles secured using PlaxidityX technology. Starting from 2021, we have more than 52 production projects and more than 100 customers. We have a global presence in Korea, Japan, Germany, France, and US. We have offices in these countries. We have more than 80 granted and pending automotive-specific cybersecurity patents. We offer end-to-end solutions, and that's why we know what are the issues that can come from the in-vehicle solutions and from the off-board. All our products are automotive grade, so we can be ASIL-B ready and provide all the documentations for the ASIL-B certification, and all the products are developed in alignment with ASPICE Level 2 requirements. And of course, we have great partnerships with leading industry players such as Microsoft, DSpace, AWS, and XP, and as you can see with AVL. We offer more than just in-vehicle. The products and services portfolio that we offer are focused on 4 different pillars: DevSecOps, vehicle protection, what we just discussed, fleet protection, also the integration that is very important with vehicle protection, and theft prevention, with our new product called VDOM that is focused on the real-time anti-theft protection, both for aftermarket and for existing OEMs. Of course, on top of that, we offer services, cybersecurity compliance, architecture, testing, and engineering. So our main focus is automotive cybersecurity. And with that, I'd like to end and maybe move into the Q&A session with, of course, the call to action. Whatever you need on this topic, don't hesitate to contact me and Javier. We would be more than happy to support you, because we realize in 50 minutes it's not enough to discuss all these topics. Thank you very much. Bye.
Thank you. Bye.